So here we are in the fourth part of additional aspects of equilibria, where we're looking at solubility equilibria and how a tiny bit can make a difference. And we're going to try sample exercise 17.11 from the textbook that we're using currently. And this says solid silver chromate is added to pure water at 25 degrees Celsius and some of the solid remains undissolved. The mixture is stirred for several days to ensure that equilibrium is achieved between the undissolved silver chromate and the solution. Analysis of the equilibrium shows that the silver ion concentration is 1.3 times 10 to the negative fourth molar. Assuming that the silver chromate solution is saturated and that there are no other unimportant equilibria, calculate the Ksp for this compound. So sample exercise 17.11 starts with this solid dissolved in solution, and then it gives us just a little bit of silver ion that's dissolved. We want to know what is the Ksp for this creature right here. Step number one, when in doubt, write the reaction. And so we'll write the dissolving equation of silver chromate. It gives us 2 silver ions and it gives us a chromate anion. After we do that, we want to calculate using the coefficients how much of each is dissolved. We're told that we have 1.3 times 10 to the negative fourth silvers right here. And you'll notice for every 2 of these silvers, there's 1 chromate anion. And so we'll have to set up a relationship saying that for every 1 chromate, there are 2 silvers. So notice I'm using the stoichiometric relationship right here to give me the amount of chromate. And chromate ends up having 6.5 times 10 to the negative fifth. Now, once we know the concentration of both ions right here, now we can write the Ksp expression and we can put the concentrations in to solve for it. So the Ksp expression would be products divided by 1, because remember this is a solid, to the power of the coefficients. So Ag would be to the second power, chromate would be to the first power, and now the last step, plug the values in. And for silver, I'd plug in 1.3 times 10 to the negative fourth, square it, because there's a square here, and then for chromate, I'd put in 6.5 times 10 to the negative fifth, square that, multiply it by this, and we end up with a Ksp of 1.1 times 10 to the negative 12th. So there's an example problem where they give you some solubility information and they ask you to find Ksp. Let's do a second example problem now. And in this one, what they're going to do is they're going to ask you to calculate the solubility by knowing the Ksp. So it's actually going backwards from this problem. So this is sample exercise 17.12 from your current textbook that we're using. And it says the Ksp of calcium fluoride is 3.9 times 10 to the negative 11th at 25 degrees Celsius. And I don't say this enough, but of course if we change the temperature, we would change the Ksp, or we would change the solubility. And if you look on your Appendix D chart, notice it's always at 25 degrees Celsius. And we don't have a calculation for how that would change, but there are tables of how temperature affects solubility. Many graphs or solubility curves that would show that as well. So calculate the solubility of calcium fluoride in grams per liter. So now we're looking for the solubility, not the molar solubility. We'll find that first, but then we want to find the number of grams that are dissolved per liter for this. So stepping away, let's take a look at the steps to do this problem. Write the dissolving equation is always the first thing we want to do, just like with any of these other additional aspects right here. Always write the thing that doesn't dissolve, or the weak acid, or the weak base, or the conjugate weak acid or base reacting with water. In this case, we know that it's dissolving in water, but we're starting with the solid. So write down CaF2 solid, and then break it up into its 2 ions. Next, make an ice table. And for this ice table, remember, since it's a solid, we're going to have none, none, and none right here. And then over here on this side, we start with 0, but then we're going to have to use a variable x to decide how much of each of these is going to dissolve, because ultimately we want to know this concentration right here and then convert that to grams per liter. And so we'll get X amount of this, and we'll get 2X amount of this. And then in the end, 0 plus X gives us X, and 0 plus 2X gives us 2X right here. So once we have the ice table completed, then we can write the K, or the equilibrium constant, the Ksp for this reaction, products to the power of coefficients divided by 1. So the products are calcium to the first power, fluoride to the second power. Calcium, we'll put an X in for that. Fluoride, we'll put a 2X in for that, but don't forget to square that. So be careful how you write this, 2X squared. Then you'll need to take and square the 2 and square the X, and then multiply it by X, so it ends up being 4X cubed. And this is equal to the Ksp, which is given to us in the problem. And now we can solve for X by dividing both sides by 4 and taking the cube root. So when we solve for X, we end up with 2.1 times 10 to the negative 4th moles per liter. And notice that this is the molar solubility. Now we have to convert to the grams per liter. We're in moles per liter right now, but we want grams per liter. And the one that I want to choose is the one up here, the ion up here, that has a 1-to-1 ratio here with the calcium fluoride. And so I'll take my 2.1 times 10 to the negative 4th, and then for calcium fluoride, adding that up, there's 78.1 grams in 1 mole of the calcium fluoride. And then my 2.1 times 10 to the negative 4th times 78 gives me 1.6 times 10 to the negative 2nd grams per liter, which is my solubility of calcium fluoride. My molar solubility, if they asked for that, would have just been right here, and I could have been done, but they asked for the grams per liter solubility. So before we go, let's talk a little bit about the limitations of Ksp. Ksp seems like this amazing thing that you can calculate that's going to tell you exactly how much or how many grams will dissolve. But on page 751 of your current textbook, they talk about a number of these limitation of solubility products. These deviations usually are due to electrostatic interactions between ions and solutions, what can lead ions to pair together. These interactions increase the magnitude both as the concentrations of the ions increase and as their charges increase. The solubilities calculated from Ksp tend to be low unless corrected to account for these interactions. It goes through and gives us an example about calcite and how much difference it actually makes in the real world because some of those ions actually stick together over here. And then we assume finally that the ionic compounds dissociate completely when this dissolves. But this assumption is not always valid. For example, when magnesium fluoride dissolves, it doesn't yield only magnesium and fluoride ions, but also a little bit of Mf plus ions. And so even though we write equations like this and we assume that things completely dissolve or would break up only into these ions, sometimes there's other factors along the way that affect this solubility. So what did we learn from these two video casts? We learned that there's this thing called the solubility product equilibrium constant, which remember is the products raised to the power of the coefficients divided by 1. We learned that there's this thing called solubility, and remember that solubility is in grams per liter, the mass per liter of solution. And then we learned that there's this thing called molar solubility, which would be one of these concentrations right here. And remember that's in moles per liter of solution, or the molarity.